Welcome back to Arts Learning. In this video, we're going over the hard 6.2 PDF, which includes gravitational fields, electric fields, and the triboelectric series. How to draw these fields, as well as how to compute them. Okay. This video will go deep into the hardest problems that I could find in my PDF. My PDF is linked on my website, artslearning.com, under physics section under 6.1, the unit 6.1. And it's also linked in the description below if you want to take a look at that. Okay, so let's get started. And obviously, as I usually do, I'll only go over a few questions. The others you can check out yourself if you want to. Okay, so question 4. A -2 microcoulomb charge sits at the center of a box. Two 3 microcoulomb charges sit 0.5 meters away. One up and right and one down and right. Okay. Find the net electrostatic force on the center charge. Use a symmetry and resolve each force into components and see what cancels. So this proton is going to pull this electron this way. This proton is going to pull this electron this way. If they have the same charge and they're at the same distance away from each other, right? Same distance away from the electron, that means they're going to exert the same force, but in opposite directions. So then, that means over here, right? If I broke this force up into components, these components are there. So this component and this component cancel out because they're the same vertical component, right? But these two components actually add up to give you twice as long a vector in the right direction, okay? And then from here, what can we do? Well, we can understand that since this is our twice as long right vector, we just have to compute that. And how we're going to do that is similarly, we're just going to use the Coulomb's law, right? That we first used. So let's take a look at that. Okay. Actually, let me move back to green here. Okay. So the Coulomb's law we used, force is equal to K times Q1, in this case 3, times 10 to the negative 6 coulombs, times Q2, 2 times 10 to the negative 6 coulombs, over R squared. What's your R? So here it's 0.3 across and 0.4 upward, right? If you remember your Pythagorean triple, 3, 4, 5 right triangle is the same as a 0.3, a 0.4, and a 0.5. The Pythagorean triples stay the same no matter what you divide them by. Okay, if you divide all of them by the same number. So we know that would be 0.5. And then we can say here over 0.5 squared. Okay. So what this is going to give you is approximately 0.2158 newtons of force. And this force is attractive, right? So towards each other. Towards each other. Attractive. All right? Okay. And then how we're going to find the horizontal force is we need to find the force S, right? So force S is just this force that we have, force electrostatic, times cosine of theta. So since this is our theta, this is 0.3, 0.4, cosine of theta is adjacent over hypotenuse. So it's just force electrostatic times 0.3 over 0.5. And once you do that, well, you just have to substitute in your force electrostatic and you can find your force in that direction, okay? So let's try that. 0.2158 times 0.3 and then divide that by 0.5. So approximately 1. So let me move up a bit so we can see. It's approximately, so, okay, 0.1295 newtons. Okay, but this is one of the four sets, but we know that since both of them add up, we'll have two four sets, right? So 2 times this is 2 times this, and our total force total, which is just 2 times the force in x direction, right? I just showed you why, is R 0.259 newtons. Okay, there you go. And then let's find, or actually let's start on question 5. 3 charges sit on a grid as shown, 6 microcoulomb at the origin. So here we can consider this 0, 0. Negative 3 microcoulombs at 0.4, 0. So this distance is 0.4. 2 microcoulombs at 0.4, 0.3. So for here, this distance is 0.3. Find the net electric field at point P is equal to 0, 0.3. So all the charges exert a force over here, okay? But now we're looking at the net electric field, right? Which, if you remember, was E is equal to just K times Q over R squared. So let's find that for each charge. So for this charge, let's start with this charge. The distance between these two is 0.3, and the proton emits a charge outward. So it's just going to be K, so 8.99 times 10 to the 9, and then that times, so actually let me give myself some more space here. Energy of the field, 8.99 times 10 to the 9 times 6 times 10 to the negative 9, or sorry, negative 6 coulombs, right? Micro is negative 6, and that over 0.3 squared. And this should give you about, so let's see, 8.99 times 10 to the 9 times 6 times 10 to the negative 6. So to the negative 6, right? And then divide that by 0.3, and divide that by 0.3, okay? So then this is about 599,333 newtons per coulombs, okay? Which makes sense because that's what the units are gonna be in. And now we're gonna start looking at, the other force, the other fields. So we have the field this direction, right? So this in the upward direction because proton fields point outward, right? For this proton, same thing, it's going to point to the leftward though because it's going to protrude outward, and similarly it's going to push this charge that way. So for this, energy is 8.99 times 10 to the 9 times magnitude, 2 times 10 to the negative 6, right? And then that over R squared, so we know the distance is 0.4 squared. So let's see what that looks like. Times 10 to the 9 times 2 times 10 to the negative 6, and that divided by 0.4 divided by 0.4. So approximately 112,375 newtons per coulomb. Okay, and then from that, so that's going to be our force. Actually, let me just draw it here as well. Okay, make this a bigger vector so you can see. It's going to be leftward, okay? All right. And then what about this force from this electron? So electrons pull it inward, so the force, the field vector is going to look like that. And this distance, since this is 0.3 and 0.4, I just showed you why this would be 0.5, right? So the field strength at that point is K, 8.99 times 10 to the 9, times the magnitude of this charge, 3 times 10 to the negative 6, over 0.5 squared, okay? So similarly, let's take a look at that. Times 10 to the 9 times 3 times 10 to the negative 6, and then that divided by 0.25. So that's about, let's see, what's that going to look like? That's 1,000. So 107,880 Newton per coulomb. Okay, and then but here what we're going to do is we're going to divide this into components, right? So here we have a vector like this. So this theta is going to give you your x and y components of this field. So the x component, right? So EX and then comma EY in vector format. So 107,880 times the cosine of theta is our EX, right? That's how you divide vectors. So cosine of theta is adjacent over hypotenuse, okay? So 107,880 times 0.4 over 0.5. So this should give you about, let's see, and then divide that by 0.5. 86,000, so 86,304. And then in the y direction, what's that going to look like? That's just going to be this times. So let me erase this as well. So sine theta here, and then EY. So EY is just 107,880 times, what's the sine of theta? Opposite over hypotenuse. 0.3 over 0.5. Okay, so 107,880 times 0.3 divided by 0.5. So that's 64,728. Okay, so to summarize, if you want to put it in all vectors here, this vector is in the positive y direction, okay? So we have, so this one doesn't have an x component. We have a 0, then we have a 599,333, okay? And then we have this vector, which is going the negative x direction, but 0 in the y direction. So negative 112,375, comma 0. And then we have our good old vector, right? 86,304. And then this for the y, 64,728. So I can erase that diagram now, because we have a hint of what we're looking for. So now let's just add all of these, right? So this is going to be in the x direction. What are we going to have? So we're going to have 86,304 minus 112,375. Okay. So, all right, let me do that again. 86,304 minus 112,375. Negative 26,071 in the x. And then for the y, 599,333 plus 64,728. Okay, so that's about 664,061. The magnitude, so magnitude of the E here, is going to be the square root of this squared, which is negative 26,071 squared, plus 664,061 squared. Okay, now let's look at what that looks like. 26,071 squared. And it doesn't matter whether it's negative because the negative is going to cancel out anyway, right? When you multiply two negatives, when you square them. And then you're going to add that to sit 64 O sits 1 squared. Take the square root of that. And you're going to get about, let's see. So you do that, then, okay, I almost went wrong here. I managed to catch myself right before the brink. Here, right, this is gonna be a negative. Because even though it's pulling to the positive right, it's pulling you downward in the y, okay? So, my mistake, and it just goes to show, right? You always wanna be careful when you're doing these. So 599, 333, minus 64, 728. Actually, so this is actually 534, 605. And the square root of that new expression we have, squared plus 534, 605 squared. So this squared plus 26071 squared. And then you take the square root of that. And there you go. 535, 240 Newton per coulomb. Yeah, so it took a while, but there you go. And the direction is just the arctangent of the y, 534, 605 over negative 26071. And plugging that in, you should get, okay, so you should get, so you're gonna get a value that locates you over here, right? Because arctangent is like, it's just like that. But your actual value is supposed to be over here, right? So you wanna add 180 to that value, or actually, in this case, subtract 180. Or the arctangent will give you negative, so you add 180, yeah. You add 180, and you should get 92.8 degrees, okay? So this one wouldn't be right because it's going down left, right? Down left, so no, down and right. But our vector, since we have a negative s component, is going left and up. Okay, so there you go. And then now let's look at number 9. So draw the complete electric field for the 3 charges shown, 2q, negative q, and q. Follow every field line rule. Show roughly twice as many lines on the 2q. Mark where the lines terminate, and identify any point where the field is 0. All right, so let's look. The negative q is, so how many lines do you want to do here? Let's do 5 for each charge, okay? This one would have 10 then because it's 2q. So 5 here, you would pull about, or actually let's do 6 because we need an even amount like that, right? Similarly, the protons protrude and the electrons attract, right? So the arrows are going to go like that, okay? And then these are just going to go that way. Okay, so actually this looks a bit uneven. Let me make it more clear. The reason I'm curving this arrow is because it's also gonna, if you get, remember, they're all gonna attract backwards here, right? So, but I can't do that because I don't have enough lines for that. All right, and then here you can say, same story, but you have to draw twice as many lines. So I have 6 here, but now I'm gonna draw 12, right? So we have 1 going that way. 1, 2, 3, 4, 5, 6. 1, 2, 3. And then almost like that. Then so a bit stuck there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I need a 12th one. So let's actually, because this one is going to dominate the space, right? This is a larger charge. It'll look like that, and this is going to look like that. All right. And then let's see. Okay. So yeah, the electron takes in the charges. The other two emit their charges. And half of the 2q lines curve away to infinity. Okay, seems all good. Yeah, it looks good. It looks pretty good. And then we need to draw, I believe we need to draw the, so mark where lines terminate, build that just arrows, right? And identify any point where the field is 0. So that's a bit hard, but let me show you how you do it. Okay. This is just an approximation, okay? So don't take it too seriously. But you'd have to look at the 9 here. And then the null point is going to be beyond the negative q. So maybe, so this is just an approximation, right? This 2q is going to have a large pool. This negative q and this q. So maybe somewhere over here. These two would cancel out. And then actually no. This one has to be also canceled out accordingly, right? So it's probably going to be over here. Because this will pull it very close. These two will try, but their force will get dominated by this force. And then this force is large, right? This force is medium. And this force, because it's a large distance, is also medium. Or this one can actually be small, okay? And then accordingly, they can match up to the large and defeat it. Match it. So obviously, very rough sketch, right? But just what it is. Okay. A neutral metal sphere is brought near but not touching the negatively charged rubber rod from problem 11. Explain using field and induction why the sphere is attracted, and state the sign of charge on the near and far sides of the sphere. Okay, so I explained this in my previous video, but you might have to explain sometimes, right? So let's go over what this looks like. So even though you haven't done problem 11, you can still do this, okay? It's a negatively charged rod, so just keep in mind negative charge here. We're given a neutral metal sphere. So the metal sphere will have protons that match electrons, okay? That's how the natural state of things is. Ions don't exist very often naturally in nature. So it's gonna be balanced, right? With this thing here, suppose it has 2 protons, it has 3 electrons. So it has more negative charge than positive charge, and hence it is negatively charged, okay? But these both match up here. So what's going to happen is when you bring this rod closer, think of these two as canceling, okay? Think of these two as canceling. With this electron, you're going to repel the other electrons, right? So the electrons are going to go farther away. And what are you going to do? You're going to attract the protons. They're going to come closer to you. Okay? And there is this one instrument that I forgot the name of, but when you put your hand on it, your hair rises immediately. And you should check it out. I recommend you check it out. And this is the same principle behind why that works, okay? So that's on the near side of the sphere, we have positive charge, okay? On the far side, we have negative charge. Okay. And I just showed you why, right? The electron repels the other electrons, but it pulls the protons. And similarly, you can keep your same composition. So this is a large misconception, right? That a charged object can only attract or repel charged objects, but sometimes this is also possible. So there are some, this doesn't happen for every object, but for metal and stuff, it tends to happen more often. Okay, because metal can conduct better. Okay, the induction here is going to separate the charge, and the closer side is going to win. So don't worry too much about the induction. If you don't understand what that is, I'll go over it in one of the, I'm going to go over it in one of the newer units. Induction means you're generating charge from moving magnets, but we'll look at that, right? And well, that's it. There you go. Make sure to check out my PDF if you have any other questions you want to look for. There's more practice, more stuff we haven't, all the concepts I tried to cover my best, but there is more practice that you might want to take a look at. And we didn't really cover the triboelectric series. I guess this was sort of a subset of that. But you'd obviously want to look at these problems, okay? All right, and that's it for this video. As always, the PDF is linked in the description. Make sure to check it out for resources on knotslearning.com. And that's it for this unit. We're going to conclude this unit and move on to circuits next unit, so stay tuned for that. Make sure to subscribe so you get the latest updates on circuits as well as the units that are coming forth. And you can stay tuned to your physics journey with utmost vigilance. Okay? Thank you for watching.